Hi, and welcome to my presentation on carbon dioxide and effects on our oceans. As you'll notice, some of the images come from Unsplash, which is free royalty images, as long as you give citation, and I suggest everyone go there when giving a professional presentation. So the learning objectives that we had in this class were to describe the key attributes and processes in the ocean, and to identify and explain mechanisms that drive some of those processes, as well as to analyze data and evaluate the impacts of climate change on ocean processes. So I integrated all of these into my particular project. And I wanted to go over two aspects of what in our Stewart's text they call deep circulation, and basically understanding Earth's climate and its possible response to increased carbon dioxide or CO2 in the atmosphere requires two things: the ability of cold water to store CO2 and heat absorbed from the atmosphere, as well as the ability of deep currents to modulate the heat transport from the tropics to high latitudes. Our ocean acts as a primary reservoir. The oceans have a lot of CO2 in them, and they contain 40,000 GTC, which is extremely a very large amount of carbon, these giga sizes. And it's basically dissolved, particulate, and living forms of carbon. The land, however, only consists of 2,200 GTC, and the atmosphere only contains 750. So the ocean holds 50 times more carbon than in the air. It's important to understand this. A lot of times it'll sift to it'll go to the bottom of the ocean. It can become shells and other things as well. So it isn't that carbon is evil necessarily, but that the ocean certainly holds a large burden of being a reservoir. So the most common source of acidity in water is dissolved carbon dioxide. The carbon enters the water through equilibrium with the atmosphere, and it can react with the water and create carbonic acid. That's what this second equation is showing. When it's combined with H2O, creates C2CO3, which later can become something else as well, but it can react with water to form this carbonic acid. And so only a small fraction exists as an acid. If you'll remember, that's in the tenths, hundredths, thousandths place, because it's times 10 to the negative 3. So it's a very small amount of this that exists as the acid itself. And a lot of this information, if you want a refresher for environmental chemistry, there's a really interesting course notes that you can have from Utah State University on the chemical aspects of this. Using Henry's law, we can help actually assess how much carbon dioxide is in any particular part of water. So here's just Henry's law constants. There's various constants and the moles that we can assess. And there's a really good chart available from that the Chemistry and Physics Journal. But what are the effects? So before going on to the effects, I want to mention that CO2 makes up 0.0355% of the atmosphere total. So it might seem relatively small, but we can calculate the amount of CO2 dissolved in water, which highly depends on the atmosphere and pressure. And so we use Henry's law to calculate that with any particular condition. But what are the effects? So forecasts of future climate change, this is from our textbook, depend strongly on how much CO2 is stored in the ocean for how long. So if little is stored, or if it's stored and later released back into the atmosphere, because a lot of that storage is very temporary, then the concentration in the atmosphere will change as well. So modulating Earth's long-wave radiation balance if we have too much atmospheric carbon dioxide. I want to talk about radiation absorption for a moment. And this is basically used to show the effects, I suppose, of, to summarize this, it's estimated that there's an increase in the mean temperature over time. And there's a bit more discussion in the actual paper on the atmosphere and how that can be calculated and how that flux is used. But one of the main takeaways is that we can have carbon trackers, and we can now, as opposed to maybe some of the earlier studies from the 1950s where we didn't have enough data collected on carbon in the atmosphere, we can now actually measure how many, what's the expected growth going to be year over year. And a PGC is actually a petagram. If you remember petabytes being above 1,000 terabytes and those sorts of things. But basically a petagram is a very large amount of carbon. And we can measure, we can simulate the growth over time. And with that, we can also calculate various oceanic results. For example, the surface ocean change in pH over those years. You'll notice there's a negative. So if we remember pH, below 7 is more acidic and above 7 is more of a base if we look at the solutions. So as we can tell over time, the ocean's expected to get more acidic over time. And the effects of this, the result indicates that atmospheric release of CO2 will produce changes in ocean chemistry that could very much affect marine ecosystems significantly. And there are various pathways that they model in this particular article, but there are chemical effects on the marine environment, and it may be as great a cause for concern as the radiative effects that we focus on for atmospheric CO2 when it's brought back in increased levels there. So what can we do? And I have about a minute left. We're about 7 minutes into this 8-minute presentation. Well, we can reduce the amount of, I don't want to say artificial carbon that we produce, but the amount of carbon that we produce. So we can put carbon taxes on emissions. We can use renewables like electric vehicles, wind and hydroelectric instead of coal and natural gas. We could also, and this is something I'm focusing on for my PhD program, is the avoidance of peak demand times. So again, we can use these EVs, renewables, but we can also save the amount of pounds of CO2 that we produce by not necessarily reducing our kilowatt hours of electricity used, but by being smarter with when we store it, maybe in a whole home battery when we use it. And we can reduce that peak demand, which will reduce the CO2 byproduct per kilowatt hour by avoidance of that peak demand time. I'm very interested in thinking how can we reduce our pounds of carbon in unique ways. And by reducing these carbon emissions and atmospheric pounds of carbon dioxide, the ocean will not need to be as large a temporary reserve for our carbon dioxide. Thank you so much for listening to my presentation, and I will be excited to see yours as well. Thank you.